and that will be the next subject that I will also take. Uh, so is there anything? Someone is presenting something. So all of you are have the study material that is shared from the official IGNOU site. Do you have all the study materials or the books or blogs, let's say?
Yes, sir. We have the soft copy.
Soft copy. Okay,
Yes.
then fine. So I will just share one presentation before we really go into the study material. Just to give an overview of what you expect or the what learning you will get from this particular course. So let me share a presentation first. Okay, so where is yeah. So the presentation is visible.
Yes, sir. It's visible.
Okay. Uh, so when we look at physics or study physics, so there are four realms or four domains of physics that we typically discuss or talk about. So which you are also familiar with, I hope. So one is the classical mechanics or the classical world that we see all every day around us. Then the second domain is the relativistic mechanics. Okay, so which was kind of founded by Einstein, which describes a different physical reality altogether, which we really never thought of. Okay, which only is possible when you go to very high speed. So that is the relativistic mechanics. Then another domain, which is quantum mechanics, uh, that we encounter when we go really to very small sizes. Typically, when we talk of matter at atomic scale. So this is, you go to very small size in a few nanometer or even smaller than that. So angstrom, so 10 to the power minus 9 meter or 10 to the power minus 10 meter of that order. So where quantum mechanics kind of rules. And then when you go to a very high speed and you are at a very small sizes. So there, what we see is something known as quantum field theory. Okay, so these are the basic fundamental domains of physics that when we talk about physics, this is like can be distinguished in these four domains. And all these four domains basically governed by these four fundamental forces. Gravitational, that is the interaction between masses and why we can say the universe exists. Then electromagnetism, which is one of the important forces that we actually encounter as human being in everyday life. Okay, so gravitational, of course, we are on the surface of earth, so okay, gravitational field is or force is working on us. We see moon, sun, so which are due to gravitational forces. But for our daily survival, so electromagnetic forces is the most important force. So then, of course, there is a weak force and strong force, which are only exist when you go to nucleus or atomic subatomic structure. Okay, so that means when we, like, whatever our experience or the physics that we experience can be described mostly by electromagnetic forces, and that's why this electromagnetic theory and electrodynamics that we will see is a kind of fascinating to us as a physics student. So when you think electromagnetic force means electric force or magnetic force, okay, that is clear. This is the electromagnetic force. But we also have a lot of forces like frictional forces, molecular forces, chemical forces. And if you look fundamentally, all of their origin is pretty much due to electromagnetic forces. Okay, so some kind of interaction between charges or flow of charges or a distribution of charges that actually leads to all these frictional, molecular, and chemical forces, which appears like very fundamental forces, but they are not. So fundamentally, they are all electromagnetic in nature. So to say what is electromagnetism, so it is basically the study of, let's say, electric charges. Either they can be stationary, so they don't move, so they are just sitting at any point in space and time, so no movement, no motion, or they are moving at certain speed along certain direction. Okay, so this is basically what electromagnetism is all about. Uh, and when we see this one charge or certain charge distribution, how that distribution is affecting another external charge or any other charge, whether that charge is stationary or moving. So this is everything, all these discussions will be within this electromagnetism. So one nice thing about electromagnetism is this is like a force or a interaction which does not need any physical proximity. So even if you are really far away from a charged particle, still you will experience or you will know there is another charge exist, uh, depending on the distance and the direction. So in order to really understand electromagnetism, so we need to know few, mm, what we call as the language that we need to know, or we need to speak in that language so that we can understand what electromagnetism is. So the first thing is, of course, when we talk of charge, so the next thing that we should be aware of, what is electric field due to the charge. Similarly, when we talk of flow of charges, which basically means we have a current, so then we should talk of magnetic field. So whenever we have a magnetic field, so classically we can say a magnetic field can be produced only due to a current or a flow of charges. Now those charges, when they flow at a constant velocity. Okay, so this is also most important. Then what can happen that you can have a bit, so this is all about stationary charges or charges moving at constant velocity, but this may not be the case always. So in that case, what you have is something known as a combination of electric and magnetic field that can exist simultaneously. That is what we call as a electromagnetic radiation, which is due to a time varying field or a charge which is under acceleration. Okay, so if charge is under acceleration, that means it does not have a constant velocity. So in that case, what we typically say is we have an electromagnetic radiation, which can have both electric and magnetic field. So, as like we know for any domains of physics, so what is electromagnetism can be when you handle electromagnetism or try to understand. So you need to know about forces, you need to know about fields, the potential, energy. Okay, so these are the terms which we typically use for any other domain. So this is also what we need in electromagnetism as well. So we will understand or see what we mean by force in electromagnetism, what we mean by field in electromagnetism, what is potential in electromagnetism, and what is energy. So each of these charges, when we say there is a electric field or a magnetic field associated with it, so they all carry some kind of energy with them. And this is again something which we talk in terms of some equations. Okay, so they definitely have some physical meaning, but we always deal or understand or write them using some mathematical equations. But when we look at matter, so how electromagnetism basically manifests or can be understood in matter, so there are these certain parameters which also we need to get familiar with. So these are like permittivity, permeability. So when we talk about electric circuits, resistance, capacitance, inductance, okay, these are some of the parameters that actually represents electromagnetism when we talk of a solid, a matter. Okay, so these are the things which we will refer several times during the course. So you should be, that's why get familiar with all this language that we are going to use. Now, the electromagnetic theory can be, has been, is kind of already been put into a very elegant four set of equations. Okay, so these are, this is known as Maxwell's equation. So this is like these four equations, what you see in the top. Are you familiar with any of these terms? These expressions that we have written, or you are not familiar with this, what we have written here?
We are familiar, sir, but
Familiar? So this del dot E is equal to rho by epsilon naught. So what it means is divergence of electric field is equal to, so rho is the charge density and epsilon naught is basically the permittivity.
permittivity, free space.
So free space permittivity. So similarly, you have curl of E, del cross E. So these are all vector terms. So that you should always remember. So these are all vectors. So del, this inverted triangle that we have written, del, that is a vector operator. Okay, so this is a differential operator. So these equations, four set of equations, are known as Maxwell's differential equation. And if you can, so what is expected that you should be able to write these equations for any situation, and then if you can solve, so you can find out what is the electric field or magnetic field, and that's, then you know everything about electromagnetism basically. Okay, so we will, so the first law, for example, del dot E equal to rho by epsilon naught, is known as your Gauss's law. So this is the differential form of Gauss's law. So similarly, del dot B does not have a name, but it is a similar Gauss's law for magnetic field, you can say. Then curl of E equal to minus del B by del T. So that means the curl of E, this is a differential form that we are writing. So when you change a magnetic field with time, so a time varying magnetic field produces electric field. So which is your Faraday's law. Okay. And the fourth one, curl of B equal to mu naught J plus, so up to mu naught J. So that is your Ampere's law. And then there is an extra term. We will see why this extra term that appeared in Maxwell's equation. And actually, if you look carefully, Maxwell's contribution is basically adding this final fourth or the final term on the right hand side here to the curl of B. And these, again, this Maxwell's equation can be written for free space, okay, or it can be written for a matter, okay. So inside a matter, so you have a bit of a different, uh, instead of electric field, so you have a displacement vector and so on. So we will see how this appears. But basically, in a nutshell, electromagnetic theory can be captured in this set of four differential equations. What is also expected that you should be able to not only write these differential equations, also you should be able to write these equations in integral form. So this is a differential form, then also you should be able to write it in integral form, and then give an explanation or what is the physical meaning of these equations. So once you do that, so I think you know everything about electromagnetic theory. Okay, so this is just basically why, just a continuing discussion. So we have a fundamental understanding of nature, electric or magnetic field, a nature of interaction, and electromagnetism has a lot of engineering applications. So when you think of any application that we have, so right now the way we are communicating is based on this electromagnetic wave. Okay, so we are we are able to listen to each of us, okay, and even we can see, we can communicate, okay. So all this is due to electromagnetism. So with this slide, I will just stop giving kind of a introduction what we will explore in this course. So Richard Feynman was actually one of the famous physicists. So what he said, so if you, if the human history, let's say if it survives and it looks back, let's say 10,000 years back, then, and what will be the most significant thing that has been, that people will remember in 19th century or most part of it in 20th century, is the Maxwell's discovery of the laws of electrodynamics. Okay, so this is what he said, and I think I agree with him. So that's why I have put this quote. So no one will remember any war, anything else. So the most significant thing that most likely the human history that they will remember, the significant thing or the event will be the Maxwell's laws of electrodynamics. Okay, any question? If you have, you may ask. No? Okay, so then I'll stop here. So I will share now the book that I hope you have this book with you. So just so that I know if you have this book or not, because I have this material with me.
Yes, sir,
Uh,
we have it.
this one,
Yes,
okay,
sir,
that's good.
we have the soft copy.
Soft copy, that is good. So then I will stick to this book basically, so that we are in the same. So whatever, when we talk about different principles, so we use the same language, so you will be familiar with. Then there will be no confusion. Okay, so that's why I will stick to this content, which is already kind of compiled in a nice way. But if you want, you can also read other books if you want to know more about electrodynamics. So there is a famous book that is by Griffith. Okay, the Introduction to Electrodynamics. That is considered as a very nicely written book on electrodynamics, introductory part. But there are many other books, so you can also, if you want, you can refer to those books. And if you have any question, also you can ask, or any doubt or anything, so feel free to ask. Okay, so what we will go through today and tomorrow, I think, is kind of a revision that what you know on electromagnetism. So as I said, so we will start with electrostatics. So electrostatics means how the charge or charge distribution behave when they are stationary. Okay, so this is what we will be discussing in this unit. And what are the ways we can find out the electric field due to the charge distribution? Okay. So when we think of these charges, stationary charges, and we say there is some kind of force acts on these charges, it is known as a Coulomb force. Okay, so or a electrostatic force or Coulomb force, which is given by this force, this equation 1. So let me just, this equation 1, which is F is equal to K Q1 Q2 by R square. Okay, so what is K here? K is simply a constant here. So later on we will see what exactly it is. Q1 and Q2 are the charges, and R is the distance between the charges. So this is the Coulomb or electrostatic force that acts between two charges. And of course, force is being a vector, so it must be having a direction. And what is the direction of that force? So the direction is the unit vector that joins your charge Q1 to Q2. So if you draw a, so you have a point charge here is a Q1, it is a point, another point that is charge Q2, and now the force on, so this F21 that we are seeing here. Okay, so this is the force acting on to charge 2. Uh, oh, sorry. So this is the force acting on Q1 due to the charge Q2 at a distance r. So this is the again written in a vectorial form. So Q1 Q2 by r Q1 modulo square, and this is the unit vector that starts from 1 charge Q1 up to Q2. So in this figure, basically that is described here. So if we look at the figure on this here, so this is Q1, this is Q2, and this is the unit vector R21 is defined as the force on 1 due to the charge 2, which is a line joining or a vector that joins from R from Q2 to Q1, and this is the direction of the force. Okay, so the constant that we discussed is basically this K, which is 1 by 4 pi epsilon naught, so which is again some physical constant. Once you calculate that, so it will be 8.99 10 to the power 9 Newton meter square per Coulomb. Coulomb minus 2. Okay, so this is the charge. Now, as this is a vector, so depending on whether the charge is positive or negative, So this force can be attractive or repulsive. So depending on whether the charge is positive, so if both the charges are positive, it will be a repulsive force. If one is positive, the other is negative, so the force between them will be attractive. So that means depending on the charge, so this force, the vector, the direction will change, and that will represent either a attractive or a repulsive force. Okay. So this, I think you go through this highlighted text because these are the most important things or aspects of the electromagnetism. So one thing which I will try to highlight here, something known as a superposition principle. Okay, so we can write down, of course, what is the force acting on charge Q on 2 due to Q1. So similarly here, you can also say what is the force acting on Q. So we said the force acting on Q1 due to Q2. This is the force F21. So similarly, you can also write the force acting on Q1 due to Q2. So that is also you can do. So Q2 also exerts a force on Q1 as Q1 exerts a force on Q2. This is a mutual force. So you can also write F12 as well. So here you are writing F21. So instead of that, you can also write F12. The magnitude would remain the same, but the direction will now change. So this unit vector of the direction will be different. Now if I write the force as F12, otherwise the magnitude will be the same. Okay, so one thing which is at the core of this electrostatic is known as a superposition principle. Okay, so the superposition principle is very useful here in physics. It appears in many other domains of physics as well. So in optics, even in quantum mechanics. Okay, so superposition appears quite often. And what this superposition principle means, or what it allows us to do, is basically tells us that the force, let's say there are several charges, okay? So there are there can be 10 charges, okay? And now the force acting on one due to two, let's say. So there are, so we just uh, give them names. So 1, 2, 3, 4, up to 10. So the force acting on one due to two is not getting affected by all. There are like 3, 4, 5, 6, 7, 8, 9, 10. There are other 8 charges. So this force acting on one due to two is not getting affected by any other charges that is present there. So this is like just a unique interaction or one-to-one interaction between the charges, two charges, and it does not depend on if there are any other charges exist or not. So this is what actually the superposition principle means, and that makes the life easier because we can now write down, even if we have many charges, so we can write down the total force acting on one due to all the 9 charges just as a vector sum of this force that we wrote here, this formula that we wrote here, so that we just keep on adding vectorially, of course, and then we will get the total force acting on one, charge one, due to all other 9 charges. Okay, so this is what this equation, the superposition principle, allows us to do. So we are writing now the total force Fi, which is you just add the force due to the jth charge. So there can be n such charges. So the jth charge, so Fji. So that means we are saying same charge is not interacting with itself, but with others, and it is just the product, and you have to take the summation over all these forces. That's all. So that the superposition principle allows us to calculate this resultant force, which is a vector, just by adding this individual electrostatic force that we calculate between two charges. Okay, so that is a nice thing here in electrostatic. So I think you just solve these questions. So if you have any doubt or anything, we can discuss in the next class. So these are all you do for self-assessment. So I encourage that you do that, solve yourself, and then if you feel any difficulty in solving, so you can ask in the next class. Okay, so once we know the forces, so another interesting thing is, so we talk about electric field. So this concept of electric field is also kind of unique to physics, particularly electromagnetic theory. Okay, so what this field means? So this field, now when we are defining the force, so we need to have two charges, minimum two charges. Then only we can say, okay, there is electrostatic force or a Coulomb force. But now, in order to understand how one charge behaves, so this electric field concept was introduced. So that means we can know how a charge or a one single charge behaves or affects anything else surrounding around it. Okay, so so this is what we describe in terms of an electric field. Okay, so it has a kind of uh, invisible, you can say, something exists which is invisible, but that charge has that kind of physical. So this electric field, again, it is not some imaginary thing. It is actually a real. Okay, it's a real, that real thing that exists or associated with any electric charge. Now, once we know what is the electrostatic field due to this electric charge, so we can then find out how the force or the potential, so on, that we can find out due to any other charge distribution around it. Okay, so this field will tell us if there is a charge some distance away, so how that charge will be affected due to this charge. Okay, so instead of now describing the interaction based on the charge itself, so we are describing this interaction based on uh, electric field which is due to this charge. Okay, so this is why this field concept was introduced. And by definition, as you know, so you take this electric, so this is your, you need to define a test charge and your real charge. Okay, so your real charge here is the capital Q. This is the real charge, and the test charge is a small q, and the force, again, on the test charge due to this big charge q is kq, big Q, small q, divided by r square into r cap, where r cap is the unit vector along this the position direction. So the electric field you define, that is the force divided by this magnitude of the test charge q, so which is 1 by 4 pi epsilon naught q by r square into r cap. So this is the electric field. This is how it is defined, but it is actually a physical thing that is associated with the charge. Okay, and this is how mathematically, of course, you describe it like this. And again, it is a vector quantity, so it has a magnitude as well as a direction. So what is the direction of this electric field? So magnitude is, of course, as we see, it is magnitude is given by this q by r square. So there is 4 pi epsilon naught. And what is the direction? So that, yes, any question? No? Okay, so the direction is the unit vector. So you draw a position vector from charge q to any point p where you want to find out what is the electric field. So if you want to find out, let's say, the electric field at point P, which is at a distance r, so you draw a position vector from Q to this point P, and this direction is the unit vector along that direction will give you the direction of the electric field. Of course, this direction will also depend on the whether you have a positive charge or a negative charge. Okay, so how we can see that? So you can see now, if I have a positive charge here, okay, so this is a positive charge, and the electric field is going away from basically this positive charge. So this is how the electric field is represented. Uh, the electric field is represented in reality. Okay, so this is a positive charge, the field that goes away from this positive charge. So this is the electric field. So negative, if you have a negative charge, so the electric field is basically going into this charge. So the force at any point P, so we can now define as phase charge Q multiplied by the electric field. So this is again now a mathematical representation or a relation between the force and electric field that we have just defined. Okay, so this is everything is all about one charge. But if we have more than one charge, so how do we proceed? So again, we use the superposition principle basically. So as we wrote, the force will be just the vector sum of all these forces F1, F2, which represents the force on a charge Q due to, let's say, charge distribution Q1, Q2, and so on. Okay, so this is the force. And similarly, you can also write down the electric field. Electric field also follows this superposition principle as well. So you can also write down the same way you are writing a force, you can also write down the electric field as a sum of the electric field due to these individual charges. Okay. So these are the simple mathematical extension of what we just discussed, these concepts. And okay, so then, so this is just simply some extension of that. So now we will talk about basically in electrostatics. So what we want to know is, so you can also extend this not only to discrete charge distribution, but to a continuous charge distribution. So continuous charge distribution is, instead of using a summation here that we just used here in this equation, so we used a summation over all the charges, and this is the relative position Ri minus Rj, which is the relative position between these points. So if I have a continuous charge distribution, so in that case, instead of a summation, so I will replace this summation using a integration. Okay, so this integration is again So I define this figure here. So I have a charge distribution which is continuous, and I take a small charge dq. Now I want to find out what is the electric field due to this small charge dq at point P. So that is again simple, 1 by 4 pi epsilon naught dq divided by r square into r cap. But in order to find the electric field due to the charge distribution, so I just have to add up all these small charges dq due to all these dqs, and if I take or add up all these discrete charges, so basically what I get is an integral form. So this is what we are writing for a continuous charge distribution. So 1 by 4 pi epsilon naught integration dq by r square r cap. Now this dq, how the dq is defined? So now dq depends on whether the charge is distributed on a line, on a surface, or in a volume. Okay, so depending on where the charge is distributed, so this dq will be different. So if dq is just like a point, that is like what we say as a point charge. Okay. Now, if this charge is distributed on a line, so we call it a line charge density. If it is distributed on a surface, we call it as a surface charge density. And if it is distributed, if it is distributed on a volume, so we call it a volume charge density. And accordingly, this charge dq can be written as a lambda. Okay, so lambda is basically dq or this dq is equal to lambda into dl. So it is not really clear. Oh yeah, okay. Yeah, so you can now define the charge density depending on whether the charge is distributed on line or surface or a volume. So you can define it using the charge density, and you just multiply by the length, unit length. So that is your charge density on a line charge distribution on a surface. So you write as a surface charge distribution sigma ds. So ds prime here represents the area or the surface area. dq is equal to rho r prime dv prime. So where dv prime represents your area, volume. And sometimes also people write it as a dl or dA. So d instead of ds, you can also write it as a dA small a, or dv instead of you can write d tau. Okay, so these are just some notations that people are using. So then corresponding electric field can be now in place of dq, you just simply substitute the corresponding line charge density, surface charge density, and volume charge density, and you will find what is the electric field. And of course, when you do the integral, so now for line charge, you have only so single integral you have to you have to perform. In case of surface charge density, so you have to do a double integral, and in case of volume, so you have a triple integral. Okay, so you have to integrate. So what this dv then represents? So dv is basically, when you look at the charge distribution here, dq, so we have taken something like a small cube here. So dv then represents, so this cube is defined by the length dx, dy, and dz. So that means your dv will have dx, dy, dz. So multiplication of dx, dy, and dz, and that's why you need this triple integral. So similarly, in case of area, so the area will be defined by a small unit area will be defined by dx into dy. So that's why you have to perform a double integral. And in case of line integral, of course, there will be only dx or dy or something like that. So that's why it's a single integral. Okay. So these are again, you can define it for this charge distribution for if it is uniform charge distribution. So you can take these factors out and you can just multiply it by the volume and so on. So this you can uh, check when you go through this material. So as I mentioned, so electric field is actually a real physical entity, and it exists in the space in the neighborhood of any charge or group of charge or continuous charge distribution, which is like tells you or gives a effect that okay, so there are some charges or charge distribution at this place. Okay. uh, and what basically, once we know what is the force and electric field, so what we actually want to do is we want to find out this electric field due to this any charge distribution. It can be a discrete charge, it can be a continuous charge distribution, it can be one charge, it can be many charges. So whatever charge is, so ultimately in electrostatics, what we are interested in is finding out how the charge, how the electric field due to this charge or charge distribution. Now the charge can be distributed within a line, on a line, or within a surface, or within a volume. So whatever may be the distribution, so ultimately always the goal is to find out what is the electric field. Then the next concept, so I think maybe I will take a little bit, just stop here before we proceed. So if you have any question or anything, so that we can, any equation which you did not understand or which is not clear. So before we move on.
Sir, good afternoon, sir.
Yes.
Sir, we have a WhatsApp group comprising of the official IGNO group students of around
Mhm.
500. Most of the
Around
all of the
500.
professors, yes, around is 470. But
Okay.
they are not the only the admin few 2 3 admin and professors are allowed to write them there. So all our
Mhm.
previous professors are there. I request you to join us so that as and when any kind of any kind of inputs or PDF you want to share, that can be easily shared there. Okay. In that case,
Ah,
you
okay.
can. In that case, please do share.
Or
Once you
but
all
I
yes,
was
yes.
I was thinking to form a Google Classroom.
Okay,
If
that would be
you
fine, sir.
if you are familiar with Google Classroom, so I will make a Google Classroom and you can join there. And then I can post, let's say, some assignment and some kind of like problem, so which you can solve, and we can also, so you can upload it over there. That would be better, I think.
As your choice, sir. Just that group is there with other three professors. That's why I said
Mm.
it's up to your choice.
Mm.
Obviously, you are okay to do whatever you like. That's not an
Okay.
issue, sir. Thank you.
Okay. Okay. Yes, there are some other questions. Yes.
Sir, I have doubt in volume charge distribution.
Volume charge. Okay.
Yes, sir. Yes, sir.
Uh, okay, we will go through one by one. So because I mean, since when I'm presenting, so sometimes I miss when you are typing these questions. Okay, I will go through the questions also. The volume charge. Let me go to that. So everyone has the book, I hope. Okay. So what I want that you can go through the book even before joining the class. Okay. So in that case, what will happen? As you know, like we have I mean, typically, to be uh, to be honest, so this course requires more hours. Okay, so we are completing it. Completing everything will be, I mean, in 2 hours. Okay, so everything, so which is supposed to be done in, let's say, 12 or 14 hours. So since we have such a constraint on time, so we have to move really fast. So better is like you go through the different units, and if you have some specific questions, you can just mention it, so that I just go through those topics, and we spend more time on that. Okay, because otherwise most of the equations and text what is written is quite clear. So I suggest, I mean, make it to have a better interaction. So if you go through the material before coming to the class, then it will be much easier for you to really understand what we are discussing. Okay, anyway, so you have a question on volume. What is volume charge density? Okay, so volume charge density is basically, uh, so the charge, look, when we talk of charges, it is again some a mathematical way of talking about this distribution. Okay, so when we started with electrostatic, so we said we have only one single charge, isolated charge in space, and that always we say it is like a point charge. Okay, so point charge means, again, so to give an example, what is a point charge? We say electron is a point charge, for example. Okay. Now, what is the charge? Volume charge. You can think of, let's say, a nucleus. Okay, so when you look at atom, so nucleus. So in the nucleus you have protons. So and think of a big nucleus. Okay, so gold, for example, or even palladium. Like you go to the far end of the periodic table, so you take a big atom with a big atomic number. So you have like 50 protons, or maybe 60, 80, or 100 protons you have. Now these protons, how they are distributed? So the distribution will be there. We need to define this volume charge. Okay, so then only we can say, so all have the same charge, but they are distributed randomly in some volume, in some space. Okay, although one proton you can say as a point charge, but now if I take many such 100 protons, now they are distributed in a volume. So this is why we need to define this volume charge density. Okay. Uh, so similarly, the surface charge also is important. So to give a analogy or example of that, uh, you can think of, let's say, a capacitor, for example. Okay, so I don't know if we will talk about capacitors here in this module, but in electrostatic, one problem always we talk about is capacitor. So capacitor is basically, it is nothing but you take two parallel plates. So these are metal plates, right? Which are separated by certain distance t. So then you calculate what is the capacitance and so on. Now, how the charge distribution is on a capacitor? So capacitor, the charge is always on the surface. Okay. So this is why we need to define the surface charge density. Uh, so surface would be like you take a rectangular plate, for example. Okay. So rectangular plate means you have certain area A and let's say some length and width. So you calculate what is the area, and you know. So if I know the total charge on the surface is, let's say, a big positive Q or negative, depending on which terminal you are connected to with the battery. So if it is a positive charge Q on the surface, so I can now define the surface charge density, the total charge Q divided by the area of that plate, and that will give me the surface charge density. Okay, so this is why this This is why we are defining these terms from the beginning. Line charge density does not have any such use or analogy, so to say, because in most of the practical cases in applications when we think of, mostly either we use surface charge density or volume charge density. Okay, is it clear?
Yes, sir.
Okay. There is so raised hand. So Devalina Parmanik. Yes, your question. What is your question, Devalina?
सर समझ रही हूँ.
You are anything you are missing or which is not clear?
No, clear.
Clear. Okay, good. Okay, and Sonalisa. Sonalisa has raised her hand. Sonalisa Sahu. Rajan Datta.
Good evening, sir.
Yes. Mhm.
I have posted my question in the message box.
Message box. Okay, I'll check that. There are several questions.
The first one, sir.
Yes. Electric field is conservative, which means del cross E should be 0. Okay. So you are talking about the slide, what I showed, where I showed the Maxwell's equation, right?
Yes.
Okay. This is true if the field, when we talk of electrostatic, okay. So the Maxwell's equation is talk about both electro, does not really talk of electrostatic, but electrodynamics. So when we say it is a conservative field, means curl of E has to be 0. That is correct for electrostatic case. Okay. That means when charges are not moving. So when charges are stationary. If charges are moving, basically that is related to your Faraday's law, which depends on your rate of change of your magnetic field. Okay, so there the charges are not constant; they are moving at constant velocity or some. So we will discuss, go to that in detail, maybe. So I'll discuss that. Yeah, that is a good point. Yes. Then another question is what the D called. So the D that you saw in that Maxwell's equation when we talked about, so D is a displacement vector. Okay, so this is depends. So when we talk of matter, this electric field will induce some kind of a polarization within the material, and due to this polarization, so the actual electric field is different within a matter. So mostly this is true for dielectric materials. So that's why the Maxwell's equations are a little bit modified. Okay, so you are not using the E and B field, but you use something known as a D, the electric displacement vector, and also H, which is a magnetic. So B is your magnetic field, and H is your magnetic field induction. Okay, so that those terms will be used. So give some important questions from every unit. Okay, that I can do on the Google Classroom. Okay. Questions. Do everyone have a book? Okay. Yes. So displacement vector is this will be the same. Yes, in electrostatic and electrodynamics, it will be the same. So there is no two definitions. Only one kind of displacement vector is there. On conceptual question of what exactly is an electric field. Okay, so this I will discuss that. So any other question, Raju?
Yes,
Any
sir.
question? Yes.
Sir, when we write all the questions answers in time of exams, I will discuss about matlab, all the formulas or describe the formulas. All the formulas, direct formulas and describe the formulas.
Describe the for during the exam.
Yes, sir.
I think exam. I
You
have
show,
to. I
sir,
mean,
listen. Sir, listen.
so.
You saw the direct formulas.
Ha.
Direct like E equal to 1 by 4 epsilon 0 Q1 Q2 by R square. Like direct formula, yeah, describe all the formulas in
Uh,
time of exam.
describe or derive what you are asking.
Derive, sir, derive.
Derive. No, no. There
Yes,
is. I think in the book there is no derivation. So I also don't expect you have to derive any equation unless
formula.
we do it explicitly in the class. Okay. If we do
Yes,
it,
sir.
so then yes, you have to know how to derive it. Otherwise, not.
I will remember all the formulas.
Formula, if you look, also you don't have to remember. So only you have to remember, let's say, this four Maxwell's equation, and then that will be enough. So most of the things you can solve if you know these four Maxwell's equation only.
Thank you,
You
sir.
don't have to remember everything.
Yes, sir.
Okay.
Sir,
Okay.
most of the theoretical question comes or the problems from this part,
I
sir?
think better, yeah, you should solve some numerical questions also, some problems.
In our SAQ and terminal questions, sir. So most of
Yeah,
the
yeah. So
problems.
you have this SAQ and terminal questions. So solve those because similar questions will be asked. Yeah, yeah. So don't worry too much about the formula. So if it is, so still, I'm telling you. So if you just remember the Maxwell's equation, that is good enough. Others, you can actually write it from Maxwell's equation. Okay, are you familiar with vector calculus from mathematical physics? Yes. Okay. So
Yes.
Yes, sir.
because a lot of vector calculus, vector algebra, we will use in electromagnetism. Okay. So this is not so. I'm telling you, it is not very difficult. The formula might appear difficult, but if you solve it and just so for the time being, what I say, just know all the four Maxwell's equation in free space, then you are good enough. Okay, so it is good enough to know those four equations, and then how you can write it in differential form and in integral form. I think we will do that a bit later once we reach actual Maxwell's equation. Once you do that, then it's good enough. Coordinates also will be difficult, the coordinate transformation. But I'm not sure if in the electrostatic part you have anything about coordinates. So if it comes, we will discuss at the appropriate time. Okay, so the coordinate system. Okay, so let's then move on to the topic that we started. So at least complete a few units before So tomorrow, yeah, on here. Okay, let me share that. Okay, so yeah, so right now, since we are dealing with electrostatics, so when you see this curl of E, that is always zero. So which means, so particularly when we talk about charges at rest, so we say the electric field is conservative, and that means curl of E is zero. And curl of E is zero means, so we can write this curl of E as and you know from mathematical physics, curl of a gradient is always zero. Okay. So are you familiar with this? Okay, what I do is I will
Yes.
share something else. So I stop this and I will share another notebook so that we do it here and you can follow what I'm saying. Just give me a minute. So I am going to share another screen here. Okay, so just I will write down these equations. So instead of going through the book, so the book you can open if you want. So let me share. Check if it is visible. Yeah. So you see the another screen, I'm sharing it. So this is where I will write some of the equations and what we are going to discuss. And if you want, you can keep your books also with you. Okay, so when we say the electric field, so electric field we say is a conservative field. So conservative field means we say curl of E is zero. And from mathematical physics, what you know that curl of gradient of any scalar, okay, is always zero. Okay, so here, so that is why we can define electric field as gradient of a scalar, and this scalar V we call as a potential. Okay. So now we say we have a charge or a charge distribution. It can be a discrete charge distribution or a continuous charge distribution. And that charge distribution gives rise to an electric field. But a nice thing is this electric field can be expressed as a gradient of a scalar field. Okay, so instead of now just dealing with vectors, so we can take, if we know what is the potential due to this charge distribution, so which is a scalar field, and take the gradient, so then it is easy to calculate what is the electric field. Because as you see, many of you are kind of saying, oh, there are a lot of formulas, how I calculate E. So what then people thought, so let's calculate first a scalar thing, which is a potential, and then take the gradient. Now this gradient, what is the gradient? The gradient is This is a vector operator, as you know. It is simply, I will just write down as like that. So J del by del Y plus K del by del Z. Okay, so this is your vector, the gradient, the vector operator, del operator. This is how it is defined. So now if I want to find out the gradient of V, so I will just find out what is this gradient, the partial derivative of the scalar with respect to x, y, z, and that will give me the gradient. Okay. Now the second, another interesting thing is this curl of E. When we are writing curl of E equal to 0, so we can write it also in a different way. Okay, so far we are writing curl of E. Here we wrote curl of E is equal to 0, which is a conservative field, which is a differential. So this is a differential. This is a differential form of the electric field. Now we can write it down as an integral form. So how we do that? So how we can convert this curl into an integral form? So we use, in again mathematical physics, you must be aware of, you can use something known as this is one is
So what exactly mean by conservative field?
okay, so the conservative field, okay, so this is, so this name, okay, so how do I tell you? So in classical, do you know any example from classical mechanics, conservative field?
The gravitation is conservative in it.
Yes.
It doesn't depend on path followed.
Uh, this is one thing, yes. Uh,
Work done in a closed loop is zero.
yes, that is correct. Yes. So basically, if you want to find out what is the work done due to this field or due to this force, any force around a closed loop, okay, so if you find it, I think this is what we will see uh, in an integral form actually. Or rather, yeah, I should start from integral form and then go to this curl of E. So the conservative field is like what said. So if you take or find out the work done due to this force or electric field on a closed path, so that will come out to be zero. So the total work done due to this electric field or due to this Coulomb force is zero when you take a total, take a closed path, okay? And what is normally the work done when you write down or want to find out the work done due to the electrostatic field or any force for that matter? So you will write it, this is the electric field or the conservative field that you are talking about, and you take the dot product with this small length, infinitesimal length dl, and you say this is, I'm going around a closed loop, Okay, so this circle basically this represents a closed loop which will be equal to 0. Okay, so this is what a conservative field, uh, any conservative field for that matter, means. Okay, so it can be a electrostatic field, it can be a gravitational field, or it can be any conservative field. Okay, so this is again a line. So this is what we are calling as a line integral around a closed path. Okay, so that means if I, so this is point A and this is point B, and now if I take this path, okay, so the charge, so when I move the charge from point A to point B, so I have some electric field here defined. Okay, so now I move charge Q from point A to point B along, let's say, this path. Okay, and then when I come back to for closed loop, so I come back from B to A, I can take any other path. So this E dot, so the dl will be defined by any infinitesimal length here. Okay, so this is this E dot dl term that represents, and now I integrate over the entire closed path, and that will come out to be 0. Okay, so this is the meaning of this conservative field, and this implies that why it is 0. That means if I now, in another way, if I say E dot dl going from A to B, so what is the closed loop? Closed loop is A to B, then back to B to A. So I can write this as B to, so I can say, let's say this is path 1, this is path 2. So I can say A to B, this is path 1, and this is path 2, which is equal to 0. Okay, so that means this E dot dl A to B to path 1 is equal to B to A minus, let's say, path 2 E dot dl, or I can say it is just also equal to A to B path 2 E dot dl. So this is what also like there was one answer that this integral E dot dl is path independent. Okay, so whether you are going to A, from A to B, moving the charge Q in an electric field from A to B to path 1 or path 2, both will be exactly the same. So it only depends on the point A and B. Okay, so it doesn't depend on which path you are taking when the charge, you are moving a charge in an electric field. And this is what basically gives us a definition of the potential. Okay, so this is again what we are taking is a scalar product. Okay, so E dot dl. So this gives us a potential V, which we can define as E dot dl. And when we go from any point, and this is, we say it is from any point A to B, or you can also write it, so in the book you will see it is written as any point R to small r. So this is your the point A is defined by a position vector r, and point B by a position vector small r. Okay, so this is how you can write it down. And this R is, you can say, is basically the reference point. Okay, so in that case, and normally you say reference point, you fix it at infinity. So where you say the potential is 0, and in that case, your V of R will be simply E dot dl minus E dot dl. You can say this is infinity R. So which you can simply write as V of R V of infinity, not just V of R. So this is your 0. This is your. Okay, so the potential at R, so when we think in terms of the reference, if we take the reference at infinity, so the potential at infinity is 0, and all the potential with respect to, so at any position R will be a minus V of R. Okay, so this is how we define the electric potential. And then also we can define something known as a potential difference from here. So we can write down the same integral that we are writing here. Okay, so V of R minus A to B E dot dl. So we can also write in terms of a potential difference as well. So for that, we will write as V. So let's say if I want to calculate the potential at point B, position vector B, so I will define it as, so this is my reference, this is R, and this is E dot dl. I can define the potential at any other point A. Similarly, this is my reference R, this is the position E dot dl. So I can define now a potential difference VV minus VA simply as minus R to A E dot dl minus, here again a minus sign, R to B, sorry, B, so this will be B and this will be A E dot dl. And this I can write down as minus R to B E dot dl minus A to R E dot dl, which I can then write down as minus, so R and R here reference point is the same, so I can write it as A to B E dot dl. So this is my potential difference. So when you are the potential difference between point B and point A, so this is the potential difference, you can just define based on the electric line integral of the electric field from point position vector A to position vector B. So now you can write now the electric field using whatever expression we already wrote. So which is basically either depending on the volume charge density, surface charge density, or line charge density. If you can write down E, so it will be just taking the dot product with that. And then you can find out what is the potential difference. Okay. So this definition of a potential. So here, one thing which you should remember. So we are talking something about potential. So it is not same as the potential energy. Okay. So the potential, when we talk in electrostatic, the potential is different than the potential energy. This you have to also remember. Okay. Now we can calculate this if this potential for again different charge distribution. Okay, so it can be a point charge distribution, it can be due to discrete charge distribution or a continuous charge distribution, because it is a scalar thing. So if it is a so due to a discrete charge, so we can define V is equal to Q by 4 pi epsilon naught R. Okay. So now if I take the gradient of this one, so I should get the electric field. Okay. So just you can calculate what is the minus gradient of this potential. So which is nothing but, so all other terms are your 0 gradient of 1 by R, and which will give you nothing but your electric field is R square into R cap. So you can try to calculate this gradient by yourself. Gradient of 1 by R. So gradient, you know what is, we have already defined here. Gradient function we have defined here. Gradient. And 1 by R, what is 1 by R here? So R is nothing but your x square plus y square plus z square square root of that.
Whole root.
Okay, so you just substitute that and you will find out what is the electric field. So you get, this is the electric field you will get. Okay. So this thing you can do for many other problems also. So in the book, you will find some examples of that. Try to solve those examples and get familiar with the mathematics. Here already I see some, okay, so they have used already different, okay, coordinate system. Okay. Okay, so this is, you just go through the text in the book. If you feel any difficulty, we will do that in the next class. So what I want to discuss, another thing is the application of these electrostatic, which is known as Gauss's law. Okay, so this is basically is used to calculate the charge, the electric field due to a charge distribution. Okay, so the Gauss's law is always correct, okay, always true, but it is not always applied. It is only applied in certain cases where you have some symmetric charge distribution. Okay, so what is, so what actually the Gauss's law says? So Gauss's law tells you, if I take this surface integral of the electric field around a closed surface, so this is, I'm taking a surface integral of electric field around a closed surface, so which will be equal to the total charge enclosed divided by simply the permittivity epsilon naught. So this is your Gauss's law. So this Gauss's law is used to calculate electric field in many of the cases in charge when you have certain charge distribution. And particularly it is useful if you have a symmetric charge distribution. So what?
Sir, it can be used in the square loop, sir, where the charges are situated.
So let me tell you. So symmetric charge distribution, what it means, it can be like we said, it is it can be like a circle, or in 3D you have a spherical charge distribution, or you can have a cylindrical charge distribution. Okay. So of course you can use it for a square or triangular case. So if you have a symmetric charge distribution, so you can use this Gauss's law to calculate what is the electric field due to the charge distribution. And this integral form, this surface integral, is what is called as a electric flux. Okay. So what you call it as an electric flux. So flux, whenever you hear the term flux, it means something that is going out or flowing out. Okay. And whenever we say something is flowing out, we say it is what is the flow with respect to some surface. Okay. So that's why so flow is always, we say, associated with some surface, and that's why we are defining this line integral as E dot ds over the the surface integral of electric field over a surface, and that is what we are calling as electric flux. So you can so there are some examples given in the book, so I will not do that, but you just go through those working examples, and then you will know how to use Gauss's law for different applications. So it can be used for surfaces, square surface, rectangular surface, the circular surface, triangular one, okay, all kind of surfaces it can be used. And of course, so the surface can be any arbitrary surface. Okay, so it need not be so the surface that you choose is you call as a Gaussian surface. Okay, so over which you want to perform this integral. So this is a Gaussian surface. Now the choice of the surface, which surface you should take, it is very arbitrary. It is not there is any defined way you have to take. But the choice now depends on the symmetry of a charge distribution. Okay. So for example, if I have a line charge, okay, line charge. So my Gaussian surface, I would take a cylinder as a Gaussian surface. Okay. Now, if I have a charge distribution, a volume charge distribution, so I have this charge distribution within a volume. This is my volume. So I will take some kind of a spherical, or let's say this, yeah. So the sphere as a Gaussian. So sphere here, the surface of the sphere will be my Gaussian surface. In order to calculate the electric field due to the charge distribution. So these are the some tricks that you need to know depending on the charge distribution. So there are some examples also given in the book as well. So you can solve those things and try to understand how Gaussian. I can give you more problems on Gauss's law, how Gauss's law can be used. You can try to do that. I will give some examples. So this Gauss's law that we wrote, that E dot ds. So let me just write down again. So E dot ds is equal to Q enclosed divided by epsilon naught. This, in fact, you can write it in a form which is known as the first law of Maxwell's equation, first equation, Maxwell's, due to Maxwell. So how do we do that? So here, what we will do, we will use something known as, in mathematical physics, known as a divergence theorem. So the divergence theorem, what it says, that if I take a volume integral, so I can convert it to a so the volume integral, I can convert a surface to a volume integral using this divergence theorem. Okay. Okay, so so let's see how this is equivalent to the first Maxwell's equation. So the first Maxwell's equation we wrote as del dot E equal to rho by epsilon naught. This is first Maxwell's equation. So how these two are equivalent? Okay, so let me take, so in the book, you will see how you start from here and get here. Okay, so this is, you'll find in the book. But what I will do is I will show you how you start from here and get this integral form. Okay, because in the book, this is already given, so you can do that easily. But the other way around, again, will follow something similar, but I will do that here in the class. So let's take the volume integral of both sides. So I will write down the del dot E. This is the volume integral I'm writing. So you can do like that. Okay, so this is the volume integral. On the both sides, on the left-hand side and right-hand side, I have taken volume integral simply. Now, according to my divergence theorem, so this volume integral, I can convert it to a surface integral simply using the Gauss's divergence theorem. Okay, so this is, I'm using the divergence theorem. Again, we are not talking about any derivation of divergence theorem or anything. So there also you can prove the theorem as well, but we are not doing that. So we are just simply using the divergence theorem. So if I have this divergence of any vector, so here, so what the theorem says, if I have a divergence of any vector, and I'm taking a volume integral over that, so this is simply the surface integral of that vector. So this is the vector quantity E over a surface which encloses that volume. So whenever we think how you enclose a volume, in order to enclose a volume, you need the surface. Okay, so to close a volume, you need a surface basically. So this is why we are taking a closed surface integral here. And the left hand side, we are just simply now using the divergence theorem. And right hand side, So 1 by epsilon naught, I can take it out from the integral. And what is the rho dV? So rho is the charge density, right? So this is the charge density. So rho is charge density. Now, if I take the charge density and take the integral over the entire volume that is enclosed by the surface, it is nothing but all the charge enclosed within that volume by that. So this is what we now get the Gauss's differential form. So this is what we wrote. The first Maxwell's equation is Gauss's differential form. And this equation, this integral, this is the Gauss's integral form. Okay, so you can write down both and get the integral form from the differential or the differential from the integral. Both way you can do using divergence theorem. Okay, clear? And this is what you can use it now to calculate different charge distribution using different surfaces and so on. And there are several applications of this Gauss's law depending on the charge distribution or the symmetry. So you can have a spherical symmetry, cylindrical symmetry, planar symmetry. Okay, so depending on the symmetry, so you can write it in a different way, but the overall the form that we are writing is always will be correct. Only thing is what kind of Gaussian surface you choose, so that will vary or that will change depending on the charge, the kind of charge distribution. So do some of those examples in the book, and you will find how you can write a charge distribution within a volume, outside the volume, or the electric field inside a volume, outside a volume, and so on. So this is extensively kind of done in the book. So I will stop here. And what I suggest that you do this at least today, because as you know, so we are doing it in a marathon way. So so go through these exercises today, and tomorrow I will start with the energy that is associated with this electric field. So what I want to do is, first thing is you start, we can discuss some of the problems or examples. If you are try to solve that, if you are not able to solve or any step that you do not understand, so those we can discuss in tomorrow's class. And then we will talk about the third unit, basically, where we will discuss about the energy that is associated with this electric and magnetic field. And also we will see like how we can solve these how we can find a particular charge distribution or the potential due to this charge distribution. Okay, so these are some tools which we will be using to solve or find out electric field due to a charge distribution. Okay. Any questions? So I will let me just create the Google Classroom so that I will share whatever I have written down in this. I will share that material, and I'll give you what is the Google Classroom code so that you can join immediately. So if you have any question, you can also now ask. So I will post the class code in the chat box. So you just note down this class code, and you go to Google Classroom. So you have to sign in and then join this classroom using this code. So if anyone is not here today, did not join, so please inform. So if you know any of your friend or anyone who did not join, so just inform them so that they also join the classroom. So I will post like whatever I did on my this sheet here. So I'll just share that also. And anyway, go through the classroom, uh, the uh, the book that is shared with you and solve those problems. So what we will do is we will start with uh, we will start discussing if you have any issues or any problems while solving those numerical problems that is given in that book, and then we will move forward. Okay. Any question?
Eh, Excuse me, sir.
Hmm.
Sir, can you suggest a book, standard book, other than our material?
Other than you. Okay. Okay. I will post it in the classroom. Is it okay?
सर
So I can
गूगल
write here.
क्लासरूम एक ऐप है क्या?
Google Classroom, it is a like a app. So like जैसे तुम Google का you use Google Gmail जैसे use करते हो. It is another application of Google. So you just
ओके
type
सर.
Google Classroom. ठीक है? So type करो and then you say join. जब join करोगे, so first you have to log in. So you can use your, if you have a Gmail login already, so you can use that to log in into Google Classroom and then use this code that I have shared and join that classroom.
ओके सर, थैंक यू सर.
Okay. So another book that I am just writing, Griffith or Introduction to Electrodynamics by Griffith. Oh, sorry. So this is Griffith. No, I've just created. No, did you try to join with this? Wait a minute. Why it cannot? Wait a minute. Okay. Look, wait a minute. I have to change a bit setting in that Google Classroom. See setting. Down. Post and commit. It should be possible, no? Student can post. So I am posting the link. So try here. So this is the link to the classroom. So try here again. There should not be any problem. Why?
सर जॉइन
No
नहीं हो रहा
class
है
with
सर
that code
नहीं
is
हो रहा है?
there. No
नहीं
class
सर
with
नहीं
that
हो रहा है
code.
क्या बोल रहे हैं? नो
No class with that code, sir. दिख रहा है.
नो क्लास की अभी तो मैंने किया है. प्रॉब्लम क्या हो रहा है? Turned up in memory by putting apply to both the right links and class codes. Settings are fine. So
यार मीट और गूगल क्लास साइमल्टेनियसली नहीं हो सकता सर.
क्या होगा?
गूगल का मीट और गूगल का क्लास साइमल्टेनियसली यूज नहीं कर सकते सर.
No, nothing like that. I don't think so. Your account can't access this class. Switch to the current account or contact your teacher. Okay. क्या प्रॉब्लम क्या है? Analytics Google Calendar. Okay, so let me try in another. Probably is that the reason? Okay, I will. So if you are not able, so don't worry. So I will try to create another classroom. So we'll do it. I'll post it tomorrow. So if it is not, you cannot join. It is fine. So I have to figure
Okay,
out why.
this was not accessible. Okay.
This is not accessible. I understand, but I have to figure out why. So it seems there is something in the wrong in the setting. I have to change, but I don't know what. Normally it works quite well. So, but I never tried it. It's outside IIT Jodhpur, so I don't know.
It happens sometimes.
Yeah.
Thank you, sir.
Okay, ठीक है. So we will meet. Okay, one thing. So tomorrow I have a class from 12. Okay, so only for tomorrow. I think you must have received an email.
Yes sir, we have received.
Huh?
Yes sir, we have received.
So tomorrow we will have the class at 12 to 2. Okay.
Sir, from which topic tomorrow we discuss?
So tomorrow we will continue this discussion on so the second and so third and fourth unit of this book,
Sir, Laplace
and then some part of
equation.
magnetostatics also.
Sir, Laplace equation.
Laplace and Poisson's equation, and also the last unit, that is the dielectric. I think there is already how we will talk about this electric field inside dielectric materials. Okay.
Okay. Actually, sir, there was a confusion in the first schedule that which was provided to us was
Okay.
mention of your name in the very first day. Okay. Anyway, that was not there. So might be that that particular schedule
will be taken care of later on. Yes.
Which one?
That was scheduled last Tuesday, the very beginning, on the very beginning day of 2014. The PDF which was supplied by the
Okay,
office.
okay, I got. Yeah. But that has been changed actually. There is a bit
Okay.
modification. So what is right now is I will take all the classes this week almost until Friday. Okay.
Thank you,
So
sir.
except so tomorrow only 12 to 2, but rest of the days I will take it from 4 to 6. Okay.
Okay.
Only for tomorrow it is 12 to 2, and then there will be, I think, next week Monday and Tuesday I will have 2 more classes. So we will not miss any scheduled classes. Okay, so all the scheduled classes we will take. Don't worry.
Thank you, sir.
Okay.
Thank you, sir.
Okay, thank you.
Thank you, sir.
everyone. Okay, so we can stop now. So tomorrow will be 2-hour class, 12 to 2. Okay.
Yes, sir. Thank you, sir.
Thank you.